Hello friends, today we are going to discuss another very important topic of statistics which has a wide range of applications. The topic is regression. The learning outcomes of this presentation are concept of regression, meaning of simple and multiple regression, meaning of linear and curvilinear regression, construction of regression line of y on x and regression line of x on y, numerical calculations of the regression lines, the power of the regression model, coefficient of determination, properties of the regression coefficients. The term regression was first used by British biometrician Sir Francis Galton, a cousin of Charles Darwin, in studying the parent-son height relationship. The dictionary meaning of the word regression is return or going back. Regression is a statistical technique which helps us to estimate the unknown value of one variable from the known value of the related variable. However, the term regression is now used in a much broader sense. Regression analysis is extensively used in natural, social, and physical sciences, and also in business and economics for studying relationships between variables. In regression analysis, we first identify the independent variable, that is the cause, and the dependent variable, that is the effect, and try to build a mathematical model of the relationship between the variables so that we can estimate the effect for any given value of the cause. The regression analysis that studies two variables only is known as simple regression. The regression analysis that studies more than two variables is called multiple regression. The regression analysis that studies linear trend only is known as linear regression. The regression analysis that studies nonlinear trend is called curvilinear regression. Here we are dealing with simple linear regression only. Before going to the main topic, let's recall some school mathematics. Suppose we have a straight line whose equation is given by y equal to a plus bx. Here a is the intercept. It is the distance from the origin to the point where the line meets the y-axis. Here we can see that the intercept a is positive because it meets y-axis at a point above the origin 0. Again, if the line makes an angle theta in the anti-clockwise direction with the x-axis, then b is tan of theta. Here we can see that theta is an acute angle. So tan theta is positive. That means we have a positive slope. Alternatively, we can see that if we move on the line from the left to the right, we have to go upward. That means the slope is positive. So in this figure, both the intercept and the slope are positive. In the second figure, we have seen that the line meets the y-axis at a point below the origin 0. That means our intercept is negative. But the angle made by the line with the x-axis is an acute angle. So B equal to tan theta is positive. Alternatively, we can see that if we move on the line from left to the right, we have to go upward. So the slope is positive. Again, in this figure, we can see that the intercept A is positive. But the angle theta is an obtuse angle. Therefore, the slope B equal to tan theta is negative. Alternatively, If we move on the line from the left to the right, we have to go downward. Therefore, the slope is negative. So in this case, we have a positive intercept but a negative slope. Again, in the second figure, we can see that the intercept A is negative. Also, the angle theta is an obtuse angle. So, both the intercept and the slope are negative. Now, coming back to our main topic, we have learned in correlation analysis that if the correlation coefficient R equal to +1, the points of the scatter diagram will lie perfectly on a straight line with a positive slope. If R equal to -1, the points will lie perfectly on a straight line with a negative slope. If R greater than 0 and close to +1, then the points will lie near a straight line with a positive slope. And if R is negative and close to -1, then the points will lie near a straight line with a negative slope. The questions are, what is this line? How can this line be found? And what, if any, is the usefulness of this line? Answers to these questions lead us to simple linear regression analysis. Let's try to understand this with the help of an example. Suppose we have a random data of 6 pairs of observations on two variables x and y. Now let's plot the data on the xy plane. This is what our paired data looks like. If we remove the connectors, we get our scatter plot. We can see that the points show a linear trend with a positive slope. We need only 2 points to draw a straight line through them. With so many points, not all collinear, we can draw many straight lines. The question is, which line describes best the trend of the points? The line that describes best the trend of the points is called the regression line. Actually, it is the line of best fit to the points. How to obtain the line of the best fit? For this, first we have to assume one of the variables as the independent and the other as the dependent variable. Let's assume x as independent variable and y as dependent variable in our data. Then the equation of our line will be y equal to a plus bx. If we can estimate the values of a and b, then we can estimate a y for any x. The equation for this is y hat equal to a hat plus b hat x, where a hat and b hat are estimates of a and b calculated from the given data, and y hat is the estimate of y for some given x. In fact, our data gives us the regression line as y hat equal to minus 0.428 plus 0.956 into x. So this is the line we have estimated from our data. From this equation, for any given value of x, say xi, we can get an estimate of y. say yi hat. The differences between the observed values and the estimated values are called errors. Observe that the errors are on the y-axis. If we look at the paired data, we will see that the errors are parallel to the y-axis. Fitting a regression line when x is the independent and y is the dependent variable consists in minimizing the errors which are parallel to the y-axis. However, we can see that some errors are positive. In our case, blue dots are above the black dots, and some errors are negative. In this case, blue dots are below the black dots. To get away with the difficulty of signs, we minimize the sum of squares of errors. This method is known as the method of least squares. Without going to the mathematical detail, let's understand that when x is the independent and y is the dependent variable, the line of best fit obtained by minimizing the sum of squares of errors parallel to the y-axis is called the regression line of y on x. It is given by the equation y hat minus y bar equal to byx into x minus x bar, or y hat equal to y bar minus byx into x bar plus byx into x. The first term in the right hand side of the last equation is the intercept, the distance from origin to the point where the line meets the y-axis. And the first factor in the second term, byx, is the slope. In simple terms, byx is the change in y when x changes by 1 unit. It is called the regression coefficient of y on x. Now let's see what happens if we reverse the roles of the variables. That is, if we consider y as the independent and x as the dependent variable. In this case, the equation of the line will be, say, x equal to a dash plus b dash y. In fact, our data will give us a straight line as x hat equal to 4.167 plus 0.853y. This line is calculated from our data. From this equation, we get an estimate of x for any given value of y. Again, the differences between the observed values and the estimated values are the errors. Here, the errors are on the x-axis. Or, if we look at the paired data, we will see that the errors are parallel to the x-axis. When y is the independent variable and x is the dependent variable, the line obtained by minimizing the sum of squares of errors is the regression line of x on y. The equation of the regression line of x on y is given by x hat minus x bar equal to bxy into y minus y bar, or x hat equal to x bar minus bxy into y bar plus bxy into y. The First term in the right hand side of the last equation is the intercept, the distance from origin to the point where the line meets the x-axis. And the first factor in the second term, that is bxy, is the regression coefficient of x on y. It gives the change in x when y changes by 1 unit. The formulas for calculating byx and bxy are given by byx equals summation x minus x bar into y minus y bar divided by summation x minus x bar squared, and bxy equal to summation x minus x bar into y minus y bar divided by summation y minus y bar squared. So we have two regression lines. One is the regression line of y on x, the other is the regression line of x on y. So these are the regression lines calculated from our data. These lines are not interchangeable as the method of obtaining them are different. The regression line of y on x is obtained by minimizing the sum of squares of errors parallel to the y-axis, while the regression line of x on y is obtained by minimizing the sum of squares of errors parallel to the x-axis. Now let's go back to our data. Suppose we want to estimate the values of number 1 y when x equal to 40 and number 2 x when y equal to 30. In the first case, since we have to estimate y for a given value of x, we have to find the regression line of y on x. And in the second case, since we have to estimate x for a given value of y, we have to find the regression line of x on y. Now let's see the calculation steps. First, we write the values of x in a column and find the total, that is summation x. Similarly, in the adjacent column, we write the values of y and find the total, that is summation y. Then we calculate the mean of x bar, that is summation x by n. In this case it is 124 by 6 equal to 20.67. Similarly, we calculate the mean of y bar, summation y by n, and in this case it is 116 by 6 equal to 19.33. Then we subtract x bar from each value of x and y bar from each value of y. Note that these total are zeros. Then we square each x minus x bar and find the sum, that is summation x minus x bar squared. Similarly, we square each y minus y bar and find the sum, that is summation y minus y bar squared. Then we multiply each x minus x bar with the corresponding y minus y bar and find the sum, that is summation x minus x bar into y minus y bar. The regression coefficient of y on x is obtained by putting our calculated values in the formula for byx, and the result comes out to be 0.956. Therefore, the regression line of y on x is y hat equal to y bar minus byx into x bar plus byx into x. And putting our calculated values in this formula, we find that y hat equal to minus 0.428 plus 0.956 into x. And finally, if in the last formula we put x equal to 40, we get the estimated y when x equal to 40, and this comes out to be 37.81. The regression coefficient of x on y is obtained by putting our calculated values in the formula for bxy, and this comes out to be 0.853. The regression line of x on y is therefore x hat equal to x bar minus bxy into y bar plus bxy into y, and if we put our calculated values in this formula, we find x hat equal to 4.167 plus 0.853 into y. Now in this equation, if we put y equal to 30, then we get the estimated value of x when y equal to 30, and it comes out to be 29.75. Now let's see how good a regression model is in estimating the values of the dependent variable. Suppose we have two scatter diagrams. We observe that the scatter of the data points in the first diagram is much less than the second. That means correlation between the variables of the first diagram is much stronger than the correlation in the second diagram. We will find that the correlation coefficient calculated from the data points of the first diagram will be very close to +1. But the correlation coefficient of the second diagram is not very close to +1. If we draw the regression lines, we will see that the errors in the first diagram are much less than the errors in the second diagram. In the first diagram, correlation is strong and the regression line gives better estimates. In the second diagram, correlation is weak and it does not give better estimates. That is, somehow correlation is related to the estimating power of the regression model. The errors are the quantities not explained by the regression model. The total unexplained variations in y is given by sum of the squares of the errors, that is summation yi minus y hat squared. The total variations in y is given by summation yi minus y bar squared. The total explained variations in y is obtained by subtracting the total unexplained variations in y from the total variations in y. The strength of the regression model is given by the ratio explained variation by total variation. And if we simplify this expression, then we will find that it is equal to r squared, the square of the correlation coefficient. This is called the coefficient of determination. The closer r square to 1, the more stronger our regression line is. Now coming to our original data, if we put the values of x in the equation for the regression line of y on x, we get the estimated values of y, which are given in the column headed by y hat. The difference between y and y hat is the error. So we have calculated the errors and then we square the errors and find their sum. From our earlier table, we also have the summation y minus y bar square And if we put these values in the formula for R square, it comes out to be 0.82. That is, 82% of the total variations in Y is explained by the regression line of Y on X. Now, if we calculate the correlation coefficient R by our earlier formula, we will find that it is equal to 0.903. And note that the square of 0.903 is equal to 0.82. You don't have to do all those calculations if you once calculated the regression coefficients and know their properties. Note that byx into bxy equal to 0.956 into 0.853, which is equal to 0.82. So it is the value of R square as we have calculated earlier. Therefore, the product of the regression coefficients is the coefficient of determination. And from here, we can find out the correlation coefficient, which is minus plus square root of byx into bxy. So here are the properties. The regression coefficients have the same sign. If one is positive, the other must be positive. And if one is negative, the other must be negative. The product of the regression coefficients is the coefficient of determination. It is always less than equal to 1 as R lies between minus 1 and plus 1. The regression coefficient and the correlation coefficient have the same sign. So the sign before the square root should be plus if the regression coefficients are positive and minus if they are negative. That's all for today. Thank you. You can contact me through my email srmrjn@gmail.com.